we have a definition for dot product. We know that U dot V is equal to the magnitude of U times the magnitude of V cosine of theta, where theta is the angle between the two vectors. But we may not always have the angle between the two vectors. What we want to do is to find a definition for the dot product that actually uses the component form of the vectors. So now recall back in trig, when you had a triangle that was not a right triangle, you still had a relationship between the angles and the sides. Let's call this angle A, B, C, and we'll use little a, B, C to denote the lengths of the sides opposite those angles. The law of cosines states that C squared is equal to A squared plus B squared minus 2AB cosine of the angle C. So we're going to use that, but if we're going to be referring to the sides being vectors, then when we look at A squared, B squared, we need to look at the lengths of those vectors in that formula. So using law of cosines with the vectors U and V, and then remember that U minus V will be this vector that's formed by starting at the tip of V going to the tip of U. So applying the law of cosines, I know that the U magnitude of U minus V, which is the length of this side, squared, will be equal to this side's magnitude squared plus this side's magnitude squared minus 2 times the magnitude of U times the magnitude of V times cosine of the angle that's between the two vectors, theta. Now, magnitude of U, magnitude of V, cosine of theta is another thing, is the same thing as U dot V. I'm going to change the magnitude of U. Recall the magnitude of U would be equal to the square root of U1 squared plus U2 squared plus U3 squared. So the magnitude of U squared will just be U1 squared plus U2 squared plus U3 squared. And the magnitude of V, which is the square root of V1 squared plus V2 squared plus V3 squared, the magnitude of V squared will be V1 squared plus V2 squared plus V3 squared. Now U minus V would be the vector U1 minus V1, U2 minus V2, U3 minus V3. So the magnitude of U minus V squared will be U1 minus V1 squared plus U2 minus V2 squared plus U3 minus V3 squared. So now expanding the left side here, we get U1 squared minus 2U1 V1 plus V1 squared plus U2 squared minus 2U2 V2 plus V2 squared plus U3 squared minus 2U3 V3 plus V3 squared equal to U1 squared plus U2 squared plus U3 squared plus V1 squared plus V2 squared plus V3 squared minus 2 times U dot V. And now a lot of stuff's going to cancel. We have U1 squared, we have U2 squared, we have U3 squared, V1 squared, V2 squared, V3 squared. Now notice everything left over on this left side has a -2 for a factor. -2 times u1 v1 plus u2 v2 plus u3 v3 equal to -2 times u dot v, which means then that u dot v is equal to u1 v1 plus u2 v2 plus u3 v3. And that's probably the form that you've seen for the dot product if you've learned it in the past. So now all we need is the components of u and v to be able to find the dot product. Now, some of the properties of dot products is that u dot v would be the same as v dot u, and that follows just automatically from what we just found for a way to compute the dot product. And that's because it doesn't matter if you say u1 u2 or u1 v1 or v1 u1. We have commutative property in real numbers, so we do have a commutative property for the dot product. Also, if you have a scalar c times a dot product, that's the same as if you took that scalar times the vector u and then took the dot product with v, or if you took the scalar times v and then with the left dot product of u. And that's called an associative property for the dot products. If you have a dot product of a vector with a sum of two vectors, that will also be equivalent to u dot v plus u dot w, which is a form of a distributive property for the dot product. Now, let's find u dot v using the components. Here we're given that u is the square root of 3, 1, 0, and v is 1, the square root of 3, 0. We don't need to draw those two vectors in the plane and figure out the angle between them. Now we have a definition or an alternative form for the dot product which just uses the components. So u dot v will be the first components multiplied plus the second components multiplied plus the third components multiplied. So we get the square root of 3 plus the square root of 3, which is just 2 times the square root of 3. So that'll be the dot product u dot v. Find the angle between u and v. Well, we know that u dot v is the magnitude of u times the magnitude of v times cosine of the angle between them. So if we want to actually find the angle between them, we can do so by solving this equation for cosine of theta. We'll have cosine of theta equal to u dot v over the product of the magnitudes. And we can use that since we now know what the dot product of u and v is. We have cosine of theta is 2 times the square root of 3 over the product of the magnitudes. Well, the magnitude of u will be the square root of the square root of 3 squared plus 1 squared, which is 2. And the magnitude of v will be the square root of 1 squared plus the square root of 3 squared, which is also 2. So we have the cosine of theta is the square root of 3 over 2, and we know that the angle theta that's between 0 and pi that has cosine with a value of square root of 3 over 2 would be 30 degrees or pi over 6. So we can use this formula, which is just rearranging that definition of the dot product, to find the angle between two vectors. Now let's find the angle between u and w. We know that cosine of theta is the dot product with u and w over the product of their magnitudes. Well, let's find the magnitude of w. Be the square root of 1 squared plus the square root of 3 squared plus 2 times the square root of 3 squared, which is 4 times 3, which is 12. So that'll be 1 plus 3 plus 12, which is the square root of 16, which is 4. So u dot w will be the product of the components, so the square root of 3 times 1 plus 1 times the square root of 3 plus 0 times 2 times the square root of 3 over the magnitude of u is 2, the magnitude of w is 4, so we have 2 times the square root of 3 over 8, which is the square root of 3 over 4. So that means that theta is equal to inverse cosine of the square root of 3 over 4, which in radian mode would be 1.12 approximately, which is also approximately 64.3 degrees.